Okay, today we're going to be working with P.6. It's the last section in chapter P. We're working with rational expressions. Rational expression is called a rational expression because it has a ratio of two polynomials. So on top you'll see an x with some stuff going on, and then on the bottom you'll see that as well. Notice the top has x squared, bottom has x. That doesn't matter right now. We're not getting too carried away. But we have a numerator, we have a denominator, so we have a rational expression. Now the domain, this is important. The domain for a rational expression is the set of real numbers for which an algebraic expression is defined. Any value that causes the rational expression to become undefined is restricted from the domain. What we're going to look at is what are we not allowed to use. Okay, so that's what the focus is. What doesn't belong. Okay, so it all comes back to this idea of dividing by zero. If we take just a simple shape, let's take a circle. We draw a circle in, and we say that we want to cut it in half. We could easily draw a line to cut it in half. And then if we cut it again, we cut it into 4 pieces, and 8 or 6 and 8, and we can keep cutting over and over and over again, adding more and more pieces to the puzzle or to the pie. But what we can never do is cut something in a way that it produces 0 pieces. Every time I cut it, I'm just going to create more parts or more pieces. So dividing something continues to make more and more pieces, never produces 0 pieces. And so the concept of dividing by 0 is mathematically undefined, or something we don't have a definition for. So if we look at these two problems, let's look here and let's try to figure out what should we exclude from the data, or from the domain. And so we're looking at what would make this turn into 4 divided by 0. That's the question. What x values would make the bottom of the fraction 0? And so if we just let the bottom equal 0 and we add 2 to both sides, we get that x would equal 2. And so we know that this is not a good thing, because if I put 2 in there, 2 minus 2 is 0, and I get a problem. And so I'm going to say that x cannot be equal to 2. That would be the domain of this expression, or this function. Down here, when I look at the next problem, okay, we have x over x squared minus 1. The fact that this is x squared makes me think about factoring, which we talked about in the past. And in fact, this looks a lot like a difference of 2 squares. And so this does factor as x plus 1 and x minus 1. Well, what would make either or both of them 0? Here, if x was negative 1 plus 1 would be 0. And 0 times whatever's over here would turn out to be 0. But at the same time, if x over here was a positive 1, 1 minus 1 is 0. And this 0 times whatever's over here would still turn out to be 0. So in this problem, I would say that x is not allowed to be negative 1 or 1. Those are not acceptable answers, because in both cases, when you square them, they become 1 minus 1. We get 0 in the bottom. This last one, we have x plus 5. If you caught the pattern, you should know that x would not be allowed to be negative 5, because we would get an undefined result. Okay, so the key here is you cannot divide by 0. When we simplify rational expressions, sometimes the denominator can be canceled. And so what we always do is we try to factor things like we've done in the previous sections into their simplest forms. For instance, x squared minus 4x plus 3 can factor as x minus 3 and x minus 1. Why that's important is, if we look closely, we have x minus 3 on top, x minus 3 on bottom. It's important that we recognize there's a multiplication between these. So let's just think for a minute. Let's rewrite this. Let's just say that this was just 3, this was just x, and this was just 3. Wouldn't we be able to reduce those 3's? So in the same way that we could cancel and reduce there, we can cancel and reduce here. Okay, so keep that in mind as we move forward. So what we're going to do is we're going to simplify this expression, and then we'll find what needs to be excluded from the domain. Okay, that's our next goal. The way that this is stated, it actually suggests that we do this in the wrong way. I don't want to say it's wrong. This is how typically we do it, is we simplify and then we go back and look for excluded values. But even if something simplifies, we still have to exclude it from the domain. And so right now, the first thing I want to do is I want to ask the question, what would make the denominator 0? In this problem, it'd be a -1. So x cannot equal -1 is my domain, okay? I am going to state that at the very beginning, because now I don't have to worry about it at the end. No matter what happens to this problem, if it simplifies or not, I know x cannot be -1, and nothing else will matter there, okay? So first thing we want to do is we want to simplify, we want to factor everything we can, okay? So the bottom doesn't factor, it's simply x plus 1. But the top does factor. Notice how both of them have x's, and specifically they both have at least an x squared. So we say, what would be left? Well, x squared times x is x cubed, and x squared times 1 is x squared. And there we see the cancellation of the x plus 1. So the simplified version is just x squared, but with the exclusion that if you're looking for x's, you're not allowed to use -1. Down here we go again. X squared minus 1, we've seen that. That's just x plus 1 and x minus 1. So it's nice to factor. Down here, a little bit trickier. Sorry, I got carried away. I saw that and I was just so excited. I really want to know what makes this 0. And to do that, I want to factor it because it's an x squared. So I'll go x and x. Factors of 1 are 1 and 1. This tells me that the signs have to match. And in order to get a plus 2, I'd have to go plus 1, plus 1. So the thing that makes this 0 would be -1 or -1. And since both of those, okay, are the same, we're just going to say that x cannot equal -1 is our domain. Okay, every other number you could ever think of will work in this equation, but -1 does not work from the real numbers. We have to reject that value. So now we come back to the actual problem and we look for cancellations. If you notice there's an x plus 1 here and here, you cannot cancel the x plus 1 again. It's a one shot. Okay, you get to take 1 for 1, never get to double dip. Okay, so what am I left with? On top I'm left with x minus 1, on bottom I'm left with x plus 1, and that would be my simplified expression. When I say you can't double dip, it's like saying 6 over 4, because 6 is 2 times 3 over 2 times 2. I can certainly divide by 2 on top and bottom to get 3 over 2, and if you know anything about fractions, you know that's an accurate answer. What I couldn't do is to double dip and take the second 2, be left with 3. 6 divided by 4 is not 3, so this would not be an acceptable way to do that. Okay, so please be careful. We cancel one time for each piece that we have. Okay, so let's go ahead and move on. Let's look at the next section of slides. When it comes to multiplying and dividing these rational expressions, we know how to simplify them, but when we multiply or divide, a couple of things we keep track of. First, we factor everything completely. We want it in parentheses. We want to see everything in its simplest version. So, you know, if I were to go back up here, I want all this stuff factored like this, up here and down below. So that's really important. Number 2, if there's a numerator and a denominator with common factors, we cancel and wipe those out. Then we're going to multiply whatever's left together in the numerator and denominator. If we're dividing, we invert, we flip and times, or invert and multiply, then simplify the same way we did above. So here's a multiplication problem. Okay, 4x plus 8 over x squared minus 25 times x minus 5 over 5x plus 10. If I factor out what's common here, which is a 4 times x plus 2. The bottom, it's a difference of squares, x plus 5, x minus 5. The top, it's just x minus 5, that didn't change. The bottom, they both have a 5 in common, so I pull the 5 out, and it turns out I'm left with x plus 2. Canceling the x plus 2 with an x plus 2, and the x minus 5 with an x minus 5, leaves me with 4 on top, and 5 times x plus 5 on bottom. Some of you might ask, do I need to distribute? The answer to that is no. We almost never distribute the information back in. We typically leave it just the way it is. Okay? Now, if I had to give the domain here, okay, the domain, which I'm not asking you to do that right here, but if I asked you for the domain, you would have to say x could not be -5, +5, or -2, because those would make each of these parentheses 0. Okay? When we move on, what about, and so if it was division, the only difference is you would flip the second fraction and then you're back to doing the same thing. When we hit addition and subtraction, things do get a little bit messier, specifically because to add two fractions, you have to have the same denominator. In this problem, we're given problems with the same denominator, x minus 1. So we're just left to take x plus 2 minus x. We combine our like terms, which is x and negative x, to get 2 over x minus 1. If the denominators match, it is so easy. But if they do not, we must force them to match. So if we look at this next example, one problem has x plus 1 as a denominator, the other has x. And what's really important here is you cannot just add 1. Okay? The only way to adjust denominators is by multiplication. Think about this. 1/3 plus 1/2. What's the common denominator? The common denominator is 6. Well, why didn't I just add 1 to the 2 and the 1 over here and make it 2 over 3? That's never been okay. We've never done that kind of math, and so we shouldn't start doing that kind of math now. We're always going to work on multiplication of the two denominators. And so we have to get for a common denominator, our LCD in this problem is x times x plus 1. Okay, and so we say, what is this first one missing? It's missing the x from the other denominator. So we times top and bottom by x. The second equation, or second expression, it's got the x plus 1, or it's got the x, but it's missing the x plus 1. So we add that to the top and bottom by multiplication. Again, these are multiplied. Then we try to simplify. X times x minus 2 is x squared minus 2x. 3 times x plus 1 is 3x plus 3. We can combine like terms. Now, notice they multiplied the denominator together. And that's okay, but I'll tell you right now, my preferred answer here most of the time is plus 3 over x times x plus 1. On a multiple choice test question, you could see this as an answer right here. And if you left it factored like this, you might not recognize it for what it is. But if you're looking at a multiple choice test and you can't find the answer you're looking for, quick distribution would work to get you there. But yeah, either one of these would work as our answer. Well, adding and subtracting, when we don't have matching denominators, let's look at a couple more problems. One catch that comes up a lot is this subtraction. And what I want to do right now is I want to deal with this negative. Anytime this negative's here, what I'd really like to do is make it a plus and change the signs. I'm distributing. You guys remember that when you had, 3x minus 2 plus 4x, something like that, you had to distribute the negative? Same rule applies here. So this is really x over x plus 1 plus a negative 3x minus 2 all over x plus 1. This guy right here is the one that always gets left out if a mistake is made. So be careful about that. Well, now that they have the same denominator, I'm just going to combine like terms across the top. I have x plus a negative 3x. That's negative 2x. And then I have that minus 2 all over x plus 1. Now, oftentimes we get here and we stop because we're stuck. But we should always look for factoring. Is there something that factors here? These are both negative 2's. So if I pull a negative 2 out by division, negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. And that's all over x plus 1. And now I see the x plus 1's cancel. So the actual answer to this is negative 2. It's kind of interesting. There's actually not an x left. The answer is negative 2. This next example, okay, notice the denominators don't match. Well, what would the LCD be? I would need an x plus 1, but I also need an x minus 1. So in order to give both of them the same denominator, the 3 over x plus 1 was missing the x minus 1, but to put it on bottom, I must put it on top. Plus 5 over x minus 1, it needs the x plus 1. Okay. If I simplify by distribution, I'm going to get 3x minus 3 plus 5x plus 5. And because they have the same denominator, I can just put them in one fraction. X plus 1, x minus 1. Combining like terms, I get 5x and 3x, that's 8x. Negative 3 and 5, that's plus 2, all over x minus 1, x plus 1. Now I know this isn't going to reduce any significant way, but I want to try to pull out anything that's common, just out of habit. These two both have a 2, so I'm going to put 2 times 4x plus 1 over x minus 1, x plus 1. And there's my final answer on that question. There's a lot more involved when we're doing this addition subtraction, but finding the common denominator is the first piece. There's a couple of slides left. We have complex fractions, and when a complex fraction, what we're talking about is fractions within fractions. Okay? So here's an example: 4 divided by 3/6, or 2/4 divided by 8, or 3/9 divided by 4/12. All of these have fractions built inside of a fraction, and so they're called complex fractions. Now, for simplifying, typically what we do is we say multiply by the reciprocal, times 6 over 3, or times 1 over 8, or times 12 over 4. And on simple things like this, this works so well. That's all we really need to do. However, when we start using x and making expressions, it's just not that simple. For instance, this is x minus 4 over 1. So technically, I could flip in times, but look at the top. It's kind of a mess. And so what I really need to do is I need the top to be one fraction. I want one big fraction here, one big fraction here. And I want to think, what is the common denominator of all the small fractions in the problem? So this 1 is really over 1. So I'm going to look for the overall LCD. Well, this has a denominator of 4, this has a denominator of 1, and this has a denominator of 1. So the overall common denominator would be a common denominator of 4. Now this is important because I can't change the fraction. All I can do is multiply by 1. Well, if I multiply by 4 over 4, that's the same as multiplying by 1, right? But this 4 will have to distribute. And in order to distribute down here, I need parentheses. So on top, what is x times 4? The answer to that would be 4x, it's still over 4, minus 4, still over 1, all over 4 times x minus 4, all over 1. Okay? And you might say, that's weird. Why did we do that? Here's why. Right here was the payoff. What's 4x divided by 4? That's x. Minus, what's 4 over 1? Well, that's 4. Okay? Divided by, I have 4 times x minus 4. And right here you can see the x minus 4 is about to cancel. So right here is where there is a question like, well, what's the answer? I just canceled out the numerator. Well, whenever there's nothing left in the numerator, we always default with a 1, and we're going to put 4 on bottom. Hopefully this is enough to kind of give you the reminder of what you're looking at from class, also some structure for what are the steps again. Each question is going to have its own coincidences, kinks, and quirks, so you're going to have to look at those individually. But we'll see you in class, and good luck.